Well, so welcome you all to the next session of this fundamental discussion on electrical engineering. So, in the last video, we had seen that why basically we are calling a transformer, what exactly is being transformed in a transformer. Now, continuing the discussion further, we would be actually discussing that how this transformer is operating and what are the different parts that are associated with the transformer. Now, in general, if we could think of the context of our transformers arrangement, generally we used to represent the transformer something like this way. We are having the two coils having a finite number of turns. Say this is N1 and N2, the number of turns. So this is the circuit representation of a transformer where these two are the coils and this one is basically the representing the core. So depending upon the point where we are connecting the load or the source, we can have the transformer like primary winding of a transformer and secondary winding of a transformer. Now what we could do, we could connect the load and source to any of the side of a transformer. So let us try to understand that how is basically we are going to do. So suppose we are having a transformer and we are connecting source here and load here. So this is the source, this is the load. So this is the winding having n1 number of turns, this is the number winding having n2 number of turns. So the winding where basically this source is connected, it's called the primary winding or primary side of a transformer, and the other coil which is called the secondary side of a transformer. So the where the load is connected is the secondary side, where the source is connected is the primary side of a transformer. Now associated with this number of turns in the primary, there are two terms which actually describe the characteristic of a transformer. The two terms are, one is called turns ratio and the is called transformation ratio. So these two terms are actually very important, which actually used to describe the characteristic of a transformer. Generally, this turns ratio is denoted by A and transformation ratio is denoted by K. So this turns ratio is basically the ratio of the turns of the primary and secondary winding. So this is nothing but the number of turns in the primary by number of turns in the secondary. So from the arrangement what we are going to have, this should be nothing but N1 by N2. And this transformation ratio is nothing but the opposite of the turns ratio. This should be the number of turns in the secondary divided by the number of turns in the primary. So it would be nothing but N2 by N1. So this is basically the transformation ratio. Now, depending upon this turns ratio or transformation ratio, there can have three possible classification of a transformer. Now, the first one is step up transformer. The next one is step down transformer, and the third one is isolation transformer. So in step up transformer, from the name we could understand that there is a increase of something. So what actually happened that in case of this step up transformer, the number of secondary side turns is N2 should be greater than N1. So what is going to happen with K? This K should be greater than 1, or A should be less than 1. For the step down transformer there is a decrease. So what actually happened that the N2 will be less than N1. So what it would be? This K would be less than 1, or A would be greater than 1. And for isolation purpose, the number of turns in the primary and secondary side, they should be equal. So N2 should be equal to N1. So what it implies? K equal to A equal to 1. So these are the three type of transformer. Now, depending upon the application prospect, in general, what we know from Faraday's law, E is equal to N d phi dt. This is the most general equation what we are having. This minus sign is according to Lenz's law. Now we are having the transformer which is primary side and having some secondary side. So what about the voltage that would be induced in the primary? That E1 should be equal to minus N1 d phi dt, where phi being the flux in the core. This is going to happen. And what about the E2? This E2 would be nothing but minus N2 into d phi dt. So what it implies is that the voltage is induced both in the primary side as well as in the secondary side of a transformer, and the amount of voltage is proportional to the number of turns in case of a transformer. So for a step up transformer, what is going to happen? Our case is N2 should be greater than N1. So what it implies? E2 will be greater than E1. So what it implies again? That the secondary voltage will be higher than that of the primary voltage. For step down, what we are going to have? N1 will be higher than N2. So what it would happen? E1 will be greater than E2. So what it implies? That the induced voltage in the secondary will be lower than that of the primary. And what about the isolation transformer? For isolation transformer, N1 is equal to N2. So both the primary winding and secondary winding, they would be operating almost at the same voltage. So that is how basically we are going to classify the transformer. We are having different applications for different cases. That normally step up transformer is used in for transmission purpose. So what actually happened? We are having the generator here, then we are having the transformer there. So this is basically step up transformer which step up the voltage and then it come to the transmission line. At the end of the transmission line there should have a step down transformer to reduce the voltage level. So then that is going to the distribution section where again we have to use a transformer which is going to reduce the voltage level further, and then we are having our home. So generally this is what the general structure of a power system is, and the use of the step up or step down transformer is there in the practical life as well. Now the other one, that is the isolation transformer. It is going to have a different sort of example. Generally this isolation transformer is having a unique application for isolation purpose. The name itself justify that. So what is basically this isolation means? That let us suppose I am having a system here, and then we are having a transformer. Then here we are having another system. So this transformer is connected in between two systems, and suppose I want that if something coming here, some transient condition is going on in this system and this effect should not come to this particular system, so for that purpose we are going to use the isolation transformer. So although this system and this system, they would be operating in the same voltage level, but if there is some sort of disturbance in the source system, that is not reflected directly to the load system due to this transformer, because transformer is having some sort of impedance which reduces that sort of effect, and that is what the important application of this isolation transformer. So I feel that I should stop over here. If any one of you have any question, you may ask me freely. Thank you. Have a nice day.